Okay, so as I said, I will be presenting a work I did a couple months ago about benchmarking ZK-Snarks GPU acceleration. In this work, we used the library gnark in tandem with icicle. So how do I move?
Arrow down.
Arrow down. Okay. Okay, good.
Up. Or to the right.
And it's not working.
Give it a try.
Okay.
Left and right. Okay.
Okay, good. So a bit of an agenda. So I will be first introducing the work, like why are we doing this? Why does it matter? Then I will be talking a bit about how we benchmarked what we're trying to benchmark. And then finally, we'll get to geek out about some numbers and eventually try to come up with some meaningful conclusions from it. So starting with the introduction, why are we doing this? So the main idea here is that zero-knowledge proofs are very expensive and slow. Therefore, GPUs are basically used to make them faster. Now the question is it really worth it? Like, is it worth it to deploy GPU, like from a cost perspective for energy and hardware? And also, what kind of GPUs do I need? Is a GPU from a couple of generations old good enough, or do I need like the latest and greatest? So basically, when we tried to answer these questions, we couldn't find really good answers available. So the problem is that ZK-Snarks use a lot of primitives like MSMs and NTTs. And while the hardware acceleration of these primitives have been like an open field of study, the problem is that most benchmarks do not benchmark the effect on the ZK-Snark as a whole, but only on these primitives. So what we want to do in this work is to answer the question of how does GPU acceleration affect the performance of a full ZK-Snark? We also wanted to use open source software for this work. So we decided to use gnark in tandem with icicle. So gnark is basically the library we use to write the ZK-Snarks, while icicle is the implementation of the GPU acceleration. If you look at the image here, you can see how icicle is basically built. So icicle is just these primitives that are written in C, and it provides bindings for Go, Lang, and Rust. And given that gnark is written in Go, then we were able to use icicle for it. And now moving on to the benchmarking setup. As we mentioned, we wanted to see whether we could use old or new hardware, so we built two test benches for this purpose. One is a high-end test bench with NVIDIA RTX A5000, while the other one is a low-end test bench where we had multiple, I would say, old GPUs like a GTX 1060, 1070, Quadro M2000. Like, we basically wanted to know like how low can we go. For the ZK-Snark configuration, we chose the Gora16 as a backend. This is not a choice we made. That was the only implemented algorithm on the gnark library for GPU acceleration. For the circuit, we wanted something that is a bit more practical. So we chose a SHA-256 circuit where we have two inputs, the pre-image and the hash. And we basically want to prove that we know the pre-image of a already existing hash. Another thing about ZK-Snark is that there is a lot of elliptic curve arithmetic involved. So when using a ZK-Snark, you need to instantiate it on a certain curve. We went with three curves, the BN254, the BLS12377, and the BW6761. And now a quick look at how we decided on our benchmarking strategy. So the first thing we do is that we basically choose the pre-image size. We had three sizes, 32 bytes, 1 kilobyte, and 32 kilobytes. This effectively changes the size of the circuit so that we can see the effect of GPU acceleration on circuits of different sizes. Then we choose the elliptic curve and randomly generate 100 pairs of hashes and pre-images. And eventually, after running the algorithm with and without GPU acceleration, we calculate the average runtime, but we also keep track of some of the GPU stats, like the memory, the utilization, and the power. So overall, we have 18 benchmarks in total. Now, enough with that, let's move on to the numbers and the results. Starting with a bit of a spoiler, sadly, we won't be featuring any results from the low-end test bench for a number of reasons. One, some of the GPUs failed all of the benchmarks due to limited VRAM. Two, even the GPUs that managed some benchmark, none of them managed all of the benchmarks, also due to VRAM limitations. And last, last but not least, for the successful benchmarks, we had worse performance with GPU acceleration than without, which is, I know, very weird. And we tried to investigate the reason, but we could not because it was out of the scope of the work. But yeah, I mean, no, seriously. We tried benchmark. I tried looking into it, but it was maybe a bit out of my technical reach. But I would say I would blame it on icicle because it's still experimental. It was still experimental when I used it, but they had like a couple of the new versions, like since last time I used it. So I would hope it would be much better now. Starting with the most obvious, metric, which is the runtime, and as you can see here, depending on the pre-image size, the larger the pre-image, the larger the circuit, and consequently the higher the runtime. We can also see that the GPU acceleration did give us some significant speedups. I know it's not really clear in the first two pre-image sizes, but it is there if you look close enough. The other thing is that we also noticed that the choice of the curve really changes, it changes the runtime. So the larger the curve elements, so the size of the curve element is basically the last three numbers in the name of each curve. The more time it takes to run the ZK-Snark, whether that is with or without GPU acceleration. Next, we look at the circuit size. So circuit size is measured in number of constraints. So every circuit will eventually be transformed into a system of rank 1 constraints. And as you can see here, it's not really linear. It's not really proportional. So going from 32 bytes to 1 kilobyte, we get like a 4x, more constraints. And then going from 1 kilobyte to 32 kilobytes, we get around a 22x. First, we're going to benchmark the different steps of the ZK-Snark, starting with the circuit compilation and setup. As you can see, for the circuit compilation, which is the transformation of the circuit from a program to like a system of constraints, the choice of curve did not really have much of an effect. And the worst one was like around 80 seconds. However, for the setup, which is a different story. So if you take closely, you see that setup is actually in minutes, not in seconds. So especially for the 32 kilobyte pre-image size with the BW6 curve, it took almost 3 hours. Luckily, in a practical scenario, this does not matter because these steps need to be only ran once. So in a practical scenario, even if I accelerate this like a lot, it wouldn't matter because they would only be run once, and not once each new pair of inputs. Then we also wanted to see like which steps of the ZK-Snark take the most amount of runtime. As you can clearly see here, the witness generation and proof verification are nowhere to be seen. So the other two steps, which are the solution generation and the proof generation, take around 99% of the runtime. Therefore, we'll be taking a closer look on those two steps. The second thing that we wanted to look at mainly was the GPU acceleration speedup. On the left, we have the acceleration, the speedup for the full ZK-Snark. And while on the right hand, we have the proof generation speedup for only the proof generation. As you can notice, with larger circuits, we have a smaller and smaller speedup. And we also notice that the speedup is always much better for the BW6 curve. And again, that will be a common trend in this benchmark. It's basically because the larger the curve elements, the more computationally intensive it is, and the better it utilizes the GPU. Next, we want to look a bit to the GPU stats more closely. Here we look at the average memory, average and peak memory consumption. And as you can see here, while for the first two pre-image sizes it was not as large, it kind of shoots up when we go to 32 kilobytes and reaches an astounding up to 27 gigabytes of VRAM, which really only a few cards, at least in the consumer or prosumer markets, have. The other point I wanted to mention is that we looked at the memory evolution across like different runs, and what's interesting here is that the GPU memory kind of always shoots up and then comes back to a certain baseline, which means that the ZK-Snark itself does not use all of the RAM reported, but only a certain portion of it. This, like around 1,000 megabytes of RAM here in this example, is pre-allocated to some keys that are needed for computation. This is important if we want to batch, because it means that we can, in fact, put more ZK-Snarks instances to run in parallel together. The second stat we want to look at is the utilization. And here we kind of have a sort of a weird setup, where the average utilization kind of goes down with the pre-image size, but the peak utilization goes up. This is clearly indicative of the fact that the GPU is not utilized throughout the whole ZK-Snark, and it's mostly running in bursts, but at very high utilization rate. The last metric we look at is the power consumption. And again, this is more or less similar to the utilization, which makes sense because both are correlated. But it is a little less pronounced here because, as you can see, the average power consumption itself goes down with the pre-image size. But the peak power consumption also goes up, which is further indication of like these bursts that I was talking about. To confirm this hypothesis, we took a look at the evolution over 3 runs for the GPU power and utilization. And what we noticed is that although they are strongly correlated, they're not really the same. So if you look at the first 2 graphs, you'll see that although the utilization goes up and down, the power remains more or less constant. This is basically a hardware limitation where the power consumption cannot jump down directly to 0. So if it's fast enough, then the power consumption does not have time to go back to 0, although the utilization goes down to 0. However, if we look at the third curve, which is much larger in time, you can see that that when the utilization drops down to 0, the power drops down, but not quite to idle levels. So we have like some substantial power loss there, and then it eventually goes down to like these idle levels, and then it goes back up again. So these curves basically show that we have a very inefficient power use here of the GPU, not only in terms of usage, but also in terms of utilization, but also in terms of power. Looking at the power itself is not enough. We also wanted to look at this from a financial point of view, and basically we calculated the energy consumption. Now, if you look at this curve, you'll see that it's very different than that of the utilization. And the main reason for that is basically the runtime. So although we have like very similar power utilization averages, the runtimes are very different from each other. So that's why the 32 kilobytes has like a very large energy consumption when compared to the other 2. Again, back to the economy thing, to put this more in money terms, we calculated the cost of GPU acceleration for 1 million ZK-Snark runs, assuming an electricity price of 20 cents. And here are the results we came up with. And as you can see, especially for the large circuit of 32 kilobytes, these costs can be very expensive. Now, enough with the numbers. Let's try to come up with something meaningful from them. And basically, we have 4 main takeaways. The first takeaway is that the circuit is important. So the size of the circuit is crucial to the decision of whether we should employ GPU acceleration or not. And we clearly see in the numbers here that large circuits are more inefficient when using GPU and also provide less speedup. Here, we define large circuits as circuits with more than 10 million constraints. The second takeaway is that curves are also important. So depending on what curve you want to use, it would be probably more or less beneficial to invest in GPU acceleration. And like just a heads up, just that large curves are more resource intensive. So the other thing is that the curve choice also affects the GPU choice. So some curves use so much RAM that you can't even use some specific GPU models. The third takeaway goes hand in hand with the previous statements, which is that VRAM is critical, because we saw peaks of up to 27 gigabytes, which means that older GPUs are practically not usable for GPU acceleration. This could be changed if, for example, we have multi GPU support, but as far as I know, that's still not implemented in icicle. The other point that I want to mention is that not all the memory is used by the ZK-Snark. So batching multiple runs is possible, of course, with enough VRAM. So just because one run consumes 10 gigabytes does not mean that 2 runs will consume 20. And the last takeaway is that more utilization equals more efficiency. I know, seems kind of obvious. But the idea here is that GPU powers and utilization, while they are correlated, they are not the same. This means that using the GPU in bursts, as we saw in the time evolution, is inefficient compared to continuous use. Therefore, a good solution for this would be to batch all of the ZK primitives together for multiple runs and run them continuously. As with everything in life, nothing is perfect, and we had a few limitations. Of course, there was the small range of tested GPUs. And also, we did not account for CPU energy when we were making our energy calculations, so we were kind of unfair to the GPU acceleration side and made it look more expensive than what it is. We also did not do any overclocking. That's for future work, I guess. And the last thing was that proof just generated with the GPU acceleration were not valid. This was also out of the scope of this work. I tried investigating it, but I could not really come up with a very good answer. And last note I want to touch on, which is the developer experience. One of the goals of this work was to also see like the options there are for open source solutions for ZK-Snark GPU accelerations, and they were very far and few in between. Actually, this was the only setup I would say that we kind of got to work, and it was not really trivial. So in my opinion, there's still a lot of more work to do to get like to something that is deployment ready. And I also think that there's a lot of place for optimization, as clearly mentioned. Thank you, everyone. The full write-up is available on our blog if you're interested in more numbers and everything. And the code is also available if you want to run it on yourself and test your own GPUs. Thank you, everyone. That was it. And happy to take any questions.